Welcome to our channel. Watch the video until the end. Leave a like, and subscribe to the channel to support us. Our galaxy and all the surrounding matter, within a radius of tens of millions of light years, is moving at high speed towards a direction where there is something we cannot see directly. When this phenomenon was discovered in the 1980s, astronomers identified that region of space as the site of a great attractor, a large concentration of mass that exerts a strong gravitational pull on everything around it. The name chosen was very effective, because many people wonder, what really is the great attractor? At first glance, it seems something very mysterious, almost like something out of a science fiction movie. To better understand what the great attractor is, we need to take a step back and introduce the concept of peculiar velocity. Peculiar velocities, as the name suggests, might seem something abnormal. The universe is expanding, and this phenomenon causes galaxies to move away from each other according to a law called Hubble's law. This law states that the velocity at which galaxies move apart is proportional to the distance that separates them. In theory, all galaxies in the universe should follow this behavior. However, Hubble's law is an idealization that assumes a homogeneous distribution of matter in the universe, which is not the case in reality. For galaxies that are very far apart from each other, Hubble's law is an excellent approximation, but it is not perfectly valid in situations where the gravity of more concentrated mass clusters dominates over the movements due to the expansion of the universe. An example of peculiar velocity is the motion of the Andromeda galaxy, the large spiral galaxy closest to the Milky Way. Despite the general expansion of the universe, Andromeda is approaching the Milky Way at a speed of about 300 km per second and, in a period of about 5 billion years, it is expected that the two galaxies will collide and merge into a single supergalaxy. This event, despite often being described in spectacular terms, will not have dramatic effects on the stars in each galaxy, as the distance between individual stars is enormously large. Deviations from Hubble's law, as in the case of Andromeda, are not unusual and are expected to occur in areas where the density of matter is greater than average. These peculiar motions are a byproduct of the expansion of the universe and help us map the distribution of matter on a large scale, including dark matter, which we cannot directly observe. Returning to the great attractor, we can say that it is a huge mass concentration located in a zone of avoidance, behind our galaxy. The zone of avoidance is a region of space that we cannot directly observe due to the dust and stars of our galaxy that block the view. Despite these observational difficulties, studies on the motion of galaxies allow us to deduce the characteristics of the great attractor. In conclusion, the great attractor is less mysterious than the name might suggest and represents a significant source of gravity that affects the movement of galaxies in our universe. With the advancement of technology and observation techniques, we will continue to discover more about this and other extraordinary cosmic structures. In addition to the great attractor, recent discoveries have shown that this structure is also moving towards another even more massive mass concentration, the Shapley supercluster, which is one of the largest known. This discovery has broadened our understanding of cosmic scale dynamics, suggesting that there are levels of matter aggregation that go well beyond individual clusters and superclusters of galaxies, involving vast regions of the universe. The Shapley supercluster, located about 650 million light-years from Earth, is a gigantic aggregate of about 8,000 galaxies, many of which are grouped in clusters. Its enormous mass exerts a significant gravitational influence not only on the galaxies and galaxy clusters it contains but also on surrounding regions, including the great attractor and our own local group. Studying these structures and their peculiar movements provides us with valuable information about the distribution of matter in the universe, including dark matter, and the forces that govern cosmic evolution on a large scale. Mapping these gigantic structures is essential for understanding the dynamics of the universe and the role of gravitational forces in shaping its large-scale structure. Moreover, these studies help scientists refine cosmological models, such as the lambda-CDM model, which explains the accelerated expansion of the universe under the combined effect of dark matter and dark energy. Every new discovery in the field of cosmology can potentially alter our understanding of the fundamental laws that govern the universe. In summary, while the great attractor once seemed a mystery shrouded in the unknown, today we know that it is just a part of a much larger network of cosmic structures that influence the movement of galaxies on unimaginable scales. Research continues and, with the advancement of observational and analytical technologies, we can expect to discover further details on how matter is distributed and interacts throughout the universe. This continued progress in our knowledge is essential not only for understanding where we stand in the cosmos but also for appreciating the complexity and beauty of the universe that hosts us. These understandings could also have significant practical implications in the long term. For example, improved mapping and observation techniques could one day help astronomers better predict the dynamic behaviors of galaxies and galaxy clusters, providing more precise tools for studying the navigation and trajectory of intergalactic space travel, even though such applications remain well beyond our current capabilities. Observational cosmology is already beginning to benefit from new tools and more powerful telescopes. The James Webb Space Telescope, JWST, for instance, with its advanced infrared capabilities, allows astronomers to look beyond areas filled with dust and gas, like the zone of avoidance, which hinder visibility with optical telescopes. This could potentially reveal new information about the Great Attractor and other similar structures, enhancing our understanding of their nature and the influence they exert. Furthermore, the evolution of computational methods for data analysis is enabling increasingly accurate simulations of the universe. These simulations, based on principles of physics and enriched by data collected through observations, can help predict the formation and evolution of large-scale structures like superclusters and filaments of galaxies that define the texture of the universe. The future of cosmological research might also see an increasing integration between physical theories, observations, and advanced technologies. For example, research on dark matter and dark energy, which together constitute about 95% of the universe, is still largely uncharted territory. Better understanding these mysterious components could revolutionize not just cosmology but also particle physics and other areas of science. Lastly, as we continue to answer some of the deepest questions about the universe, such as its origin, ultimate fate, and the nature of time and space, we also continue to discover how vast and filled with wonders the cosmos is. Every new discovery in cosmology not only expands our knowledge but also prompts us to reflect on our position and role in this vast universe. In this context, the Great Attractor, once an enigmatic mystery, becomes a part of our collective journey towards a deeper understanding of the universe we call home.